Singular value decomposition is a powerful tool for understanding the need for and methods of regularizing least squares problems. Our objectives in this video are to analyze the impact of errors in least squares problems using the singular value decomposition. We'll introduce the idea of a truncated singular value decomposition to regularize ill-conditioned least squares problems, and then analyze ridge regression, which we've looked at before, using singular value decomposition. We know that the singular values determine the rank of a matrix. Least squares problems, which are ill-conditioned, end up having small singular values. Recall that if we're going to solve the least squares problem where we minimize the squared error between AW and D, the solution we get is A transpose A quantity inverse A transpose D. And we can take the singular value decomposition of A, and we'll assume that A is an n by p rank P matrix, and write the SVD as U sigma V transpose. This implies that W is V sigma inverse U transpose times D, where we're using the economy singular value decomposition here, so sigma is a square matrix. And we can expand this expression out as a sum. In particular, we have the sum from I equals 1 to P of 1 over sigma I VI UI transpose times D. Now if we look at the norm squared of W, we see that since the V's are orthonormal, we can pull those out, and our norm squared is simply the sum I equals 1 to P, 1 over sigma I squared times UI transpose D quantity squared. So when the singular values are small, we end up with solutions to the least squares problem that have a large norm. Now, why are large norm solutions problematic? Well, it turns out that if we have any sort of errors, then they get amplified by the norm of the solution W. So suppose that we have a solution W and now we want to use it for prediction of some sort, either for a model or perhaps we're doing classification, and in which case we would use the sign of this quantity to do a binary classifier, and assume that our feature x tilde that we measure has some error epsilon. So when we do our prediction with W, we're going to compute our predicted value y tilde as x tilde plus epsilon quantity transpose times W, and that can be written as x transpose W plus epsilon transpose W. Well, if we look at how big this term is associated with the errors in our features, we find that the magnitude squared of that term is proportional to the norm squared of W. As the norm squared of W becomes large, our solutions become very sensitive to errors. In fact, our solution could be dominated by this second term and be completely irrelevant to this first term when the norm of W becomes very large. Now, another question that comes up is, what if the rank of A is less than P? Well, in that case, we can't use this particular approach for the solution because A transpose A is not going to be invertible. And we see that over here in our expression for W, that we have 1 over sigma I. So if sigma P is equal to 0, for example, I can't take 1 over sigma P. Well, it turns out we can analyze this problem, and there ends up being no unique solution for W in this case. Let's look at a specific example of a problem where A is ill-conditioned. So let's suppose that A is 1 and then 0.99, and then in the second row we have 0.99 and 1. So this matrix is full rank, but it's close to being rank deficient. If I had, instead of 0.99, this was 1, and this was 1 down here, then this matrix would be rank 1. Now we'll just pick D to be 1 and 0.5 for convenience. And to understand this problem geometrically, we're going to consider first, what does x transpose W equals alpha? Well, this is the equation for a line. And if I graph x in the W1, W2 plane, then x transpose W equals 0 would be the set of vectors orthogonal to x and run through the origin. Now when I change to some other value, alpha besides 0, then I shift this set of vectors that are perpendicular to some other position where I cross the y-axis at the point alpha divided by x2, where that's the second coordinate of the vector x. So x transpose W equals alpha describes a line in two-dimensional space. So if we look at this problem where we have AW equals D, we see that this represents two lines. I have one line corresponding to the light blue, then I have a second line corresponding to the pink color, and the solution is where those two lines intersect. In pink, I've drawn the vector corresponding to the second row, and then in light blue, we've got the x in the first row of the matrix A. So if I look at the first equation represented by this first row of A times W equals 1, that's going to be this light blue line here where it's orthogonal to the vector 1, 0.99, and it passes through the W2 axis pretty close to 1. The line associated with the second equation in AW equals D looks something like I've drawn here. We have it's orthogonal to the vector 0.991, and it passes through the W2 axis at about 0.5. What you observe is that these two lines are not perfectly parallel because the blue and the pink vectors in A are distinct, but they're close to parallel, so the solution is actually some distance away from the origin. Eventually they will cross. So we look at this in terms of the singular value decomposition. Taking the SVD of the matrix A, I find that largest singular value, sigma 1, is 1.99. The smallest one, sigma 2, is 0.01, and therefore 1 over sigma 1, which is what plays a role in solving for the least squares problem, is approximately 0.5, while 1 over sigma 2 is 100. You can find that V1 is 1 over the square root of 2 times the vector 1, 1. So that's this vector in orange that splits the difference between the two rows of A. And then the vector V2 is orthogonal to V1, and I've drawn that down here as V2. Well, we can substitute in for D and U1, and we find that U1 transpose D is 1.5 divided by the square root of 2. Similarly, U2 transpose D ends up being 0.5 divided by the square root of 2. And when I look at W then, it's going to be given by V1, in other words, a component in this orange direction, and the length of that component is U1 transpose D divided by sigma 1. And then I also have a component in the V2 direction, and the length of that component is going to be U2 transpose D divided by sigma 2. Well, in this case, plugging in the numbers, you see that in the V1 direction, the orange vector, the length is 3/8, while in the V2 direction, the blue vector, the length becomes 25, because 1 over sigma 2 is a pretty large number. So you can see that we have a fairly small component in this direction and then a very, very large component in V2 because of the 1 over the sigma 2 term, and sigma 2 is small. And if we were to decrease sigma 2 further, we would see that the norm of W would increase even greater, because then the component in the V2 direction would increase and be even farther from the origin. Similarly, if this pink vector becomes more similar to the blue vector, in other words, if they become nearly coincident, then the line associated with the first and second equations represented by AW equals D, those lines are going to be nearly parallel, and the least squares solution is going to have a very, very large norm. As we saw in the previous slide, large norms are problematic because they lead to tremendous amplification of any noise or non-ideal effects associated with the features. Now that we understand this problem, let's look at how we might address it, again using singular value decomposition. And the first method that I want to talk about is a regularization method known as truncated singular value decomposition. And the basic idea here is that we eliminate the small singular values from the inverse. When we solve for the least squares problem, we replace the sum from I equals 1 to P of 1 over sigma I VI UI transpose D with the sum from I equals 1 to R, 1 over sigma I VI UI transpose D, where R is smaller than P. And by choosing R appropriately, we can control the level of amplification that happens due to sigma I getting smaller. So this approach not only avoids inverting the small singular values, it also can be used when some of the singular values are 0. And it's equivalent to taking our matrix A, which we wrote in terms of an SVD as the sum sigma I ui vi transpose, where I runs from 1 to p, and replacing this matrix A with a rank R approximation, sum I equals 1 to R, sigma I ui vi transpose. Of course, when we do this, we're going to increase the norm of the squared error at the solution because our W doesn't satisfy this system of equations quite as well as it did. However, we're readily accepting that increase in the error so that we can decrease the sensitivity of our solution. So how do we choose R, the number of singular values that we're going to include in the inverse? Well, one way to do this is to use some intuition and look at the size of the largest singular value and decide what kind of dynamic range, in other words, how much variability in 1 over sigma I you want. Another approach is to use cross-validation. You can split your data up into training and test sets and then average the error over the test set for different values of R and find the one that gives you the minimum test set error. So next we're going to revisit the idea of ridge regression, which we looked at previously as a method for solving problems where A was low rank or where it was ill-conditioned. And recall, in ridge regression, we minimize the squared error plus lambda times the 2 norm squared of the vector W. And by minimizing the sum of these two terms, we're effectively controlling the 2 norm of the solution and thus limiting the sensitivity. This leads to a solution for W being equal to A transpose A plus lambda I, quantity inverse, A transpose D. So if we let A be U sigma V transpose, then A transpose A is V sigma squared V transpose, and I can write lambda times the identity as V lambda times the identity V transpose, because V transpose is the identity. Taking advantage of these two definitions, I can rewrite my expression for W as V, the quantity, sigma squared plus lambda I, V transpose, inverted, times V sigma U transpose D. Well, I can take the V's out of the inverse here and rewrite this expression as V sigma plus lambda I, quantity inverse, and in here I would have had a V transpose V, and then U transpose D is the final term. Now it's worth looking at this term that I've circled, I'm going to call D here, because it's actually quite simple. Sigma squared plus lambda I inverse is a diagonal matrix, and on the diagonal it has 1 over the squared value of the singular value plus lambda. And I'm multiplying this times sigma. So this D matrix is a diagonal matrix, and on the diagonal it has elements sigma 1 divided by sigma 1 squared plus lambda, all the way down through sigma p divided by sigma p squared plus lambda. So the expression for W can be rewritten as the sum from I equals 1 to p, quantity sigma I divided by sigma I squared plus lambda, times Vi times the inner product Ui transpose D. What you see here is that by doing ridge regression, we've replaced 1 over sigma I by sigma I divided by sigma I squared plus lambda. In this case, we're not trying to invert sigma I. In fact, as sigma I goes to 0, this term, where we have the inverse, begins to approach sigma I divided by lambda. Because the sigma I squared term, we're assuming that lambda is significantly bigger than that, so we end up with being able to approximate this as sigma I divided by lambda. So we have a lot of control over the amplification of these small singular values. Now, of course, as with truncated SVD and any other regularization approach, this is going to lead to an increased value for the minimum squared error. And that's because we're no longer minimizing just the squared error. Ridge regression minimizes the sum of the squared error plus this weight times the 2 norm of the solution. So singular value decomposition is a very effective way of analyzing and understanding the impact of ill conditioning and corresponding regularization techniques for avoiding the sensitivity that results with ill conditioned problems.